Hello, good morning, everyone who is present. So still there are a couple of minutes. So we'll wait for some time and start. Okay, good morning, everyone. So this is the theorem we had stated in the last class, towards the end of the last class. So this theorem makes the intuitive notion of recurrence and transience sort of clear or more apparent. So the first part of the theorem concerns transient state. So if Y is a transient state, then we have the three conclusions listed. First conclusion is that probability that the stochastic process or the Markov chain Xn visits the state Y infinitely often is 0 for any starting point. So this is the transient state. So that process Xn coming to Y, visiting Y infinitely many times, that probability is 0, whatever may be the starting point. So the second conclusion is, starting from any point in the state space S, the number of visits to the state Y will be finite with probability 1. That is for almost all omega, that is what only for omega belonging to some set of measure 0 or something probability 0, something can fail. But invariably what this means is that the number of visits to Y will be finite. Of course, what is the number will depend on that little omega. And the third conclusion is, whatever be the starting point, the expected number of visits to Y will be finite, and it is precisely this number, rho xy divided by 1 minus rho yy. Rho xy is the probability of reaching Y at some time point starting from X. And similarly, rho yy is probability of returning to the starting point Y at some time in future. So this concerns the transient states. And concerning recurrent states. So let Y be a recurrent state. Then we have 4 conclusions listed. Here, of course, one has to be careful what the starting point is. Y is given to be a recurrent state. If you start from Y, the probability of visiting Y, that is probability of returning to Y infinitely often or infinitely many times, that probability is 1. And also the probability of number of visits being infinite. If you start from Y, number of returns to Y being infinite, that probability is also 1. And if you start from Y, the expected number of visits to Y or returns to Y is infinite. So that tells you recurring again and again and again. And what about the other starting points? Possibly some X not equal to Y. So then, if you start from such a point, then the number of visits being infinite, which is of course same thing as P sub x ty less than infinity. So, I mean, that will turn out to be. So this is not actually this thing. The number of visits being infinite, here at least once it should come. And that is this probability. This equality we know. Rho xy is precisely this. So what it basically means is that if you start from x, if you can come to y with positive probability, after that the probability of visiting y again and again is the same as this probability. So because of that, if rho xy is strictly positive, then starting from such an x, expected number of visits to y becomes infinite. All these possible visits will happen after coming to y for the first time. And if rho xy happens to be 0, that is starting from x, if you can never come to y, then certainly the number of visits or expected number of visits to y will also be 0. So this is what the theorem says, and we have this slide we have seen last class. Now we will go about proving that. Okay, so the first observation is, so we are interested in the event ny equal to infinity. Note that the sequence of events ny greater than or equal to k, that is decreasing, and it decreases to this event. In other words, ny equal to infinity is the intersection of all these kind of events, k going from 1 to infinity. And that is a decreasing sequence. So that's what we have written in English. The event, there should be a bracket here. Ny greater than or equal to k, that decreases to the event ny equal to infinity as k goes to infinity. Okay, so by lemma 1, now we know what this probability is from lemma 1 for any starting point. So use that lemma. So P sub x xn equal to y infinitely often. So that is, of course, we know that it is the same thing as P sub x ny equal to infinity. And because of this, by a result we had seen earlier when we did the prerequisites, or when we sort of reviewed probability theory. So it is the limit as k going to infinity of P sub x ny greater than or equal to k. And we know this guy, an expression for that. So that is limit k going to infinity rho xy times rho yy to the power k minus 1. So this rho yy can be equal to 1 or strictly less than 1. If it is strictly less than 1, this will go to 0 as k goes to infinity. And if this is equal to 1, the limit will be always that. There is no really variation. It will just remain rho xy. So if in this case, the proper P sub x xn equal to y infinitely often, that is 0 if rho yy is strictly less than 0, and it is rho xy if rho yy is equal to 1. Now you can verify that the first two assertions concerning the transient state and the first and the third assertion concerning the recurrent states can be. Hello? So the first and the third conclusion concerning the recurrent states follow from these things. I leave it to you to verify these. That is, these two assertions follow from what we have done so far. And similarly, this one and this one, they also follow, first and third. Yes. Did somebody say anything?
Sir, yeah, can you go to the previous slide?
You can note it down instead of asking to be going back again and again. This was shown in the last class itself.
Okay, it is fine now.
So please note it down if you want to. It will be much simpler for you to refer back to your notes than my going back to the slide. Okay. So the next part of the proof that concerns the GY, basically GXY. So that basically means one has to take expectation. So that is what we will see now. So GXY, by definition of GXY, is E sub x of ny. This expectation of this random variable if the starting point is x. And we know that ny is a random variable which takes values in the non-negative integers. So by the second question in problem set 1, we have this expression. Summation k going from 1 to infinity of p sub x ny greater than or equal to k. And for this, we have the expression from lemma 1. So it is summation k going from 1 to infinity rho xy multiplied with rho yy to the power k minus 1. Clearly, this guy is 0 if rho xy itself is 0. And if rho xy is positive and rho yy is strictly less than 1, this can concern the transience case. This would be this expression. And if rho xy is strictly positive and rho yy is equal to 1, it is clear that this summation would be infinite.
Sir, I have a question.
Yes.
So if rho xy is greater than 0 and rho y is less than 1, so why it is rho xy by 1 minus rho y? Can you explain this?
This is a geometric series. Right?
Yes. Okay, but how do you know that it will converge?
I think you should get back to your this thing concerning geometric series. A geometric series, if infinite sum, when the conditions under which it converges, you go back to and see it. If the common ratio is strictly less than 1, say here these are numbers between 0 and 1. If it is less than 1, it will converge.
Okay.
See, certain things you can easily go back and check by referring back to your analysis, basic analysis notes or basic probability notes and things like that. I expect people to work something at least after going back home. And I suppose you are, I think, already reasonably familiar with the thing in a mathematical institute. Many things you have to verify yourself. It can easily be seen that note that are all potential exercises to verify. Okay. Now I leave it to you to verify that all the remaining assertions of the theorem follow now from this. regarding convergence, things like that, yes, sometimes you can ask questions, but invariably you can spend some time to see whether from the results which you already know convergence easily follows. Usually when these things are sort of left without explaining, that's what it means. Those are easily verifiable. Okay. All right, we'll go to the next slide. So, yeah, quick observation. By definition, for any fixed x, x is either recurrent or transient. Because we have defined the concept of recurrence and transience that way. We say x is recurrent if rho xs is equal to 1, and x is transient if rho xx is strictly less than 1. So one can verify that the following corollary follows. A state y is recurrent if and only if p sub y starting from y, the process visiting y infinitely often, that probability is equal to 1, and that is equivalent to gyy equal to infinity, and which is equal to gxy equal to infinity for all x. For proving these equivalences, we may have to use both parts of the theorem. And similarly, if y is transient, so p sub x, xn equal to y is that visits infinitely often for starting point x, that probability is 0 for all x in the state space. And that is equivalent to gyy strictly less than infinity, which is equivalent to gxy less than infinity for all x. Please note it down if you want to. Yeah, now we take up this question. Suppose x is a recurrent state and a state y is accessible from x. That is, y is, y can be reached from x. X leads to, x leads to y. So then of course you suspect that since if x is a recurrent state, the Markov chain visits x infinitely often. So if from X, the Markov chain can go to Y infinitely many steps with positive probability, it should be possible from Y to return to X. And again, it goes back to Y. So you suspect that the Y also should be recurrent. And not only that, in this case, rho XY as well as rho YX, both are also equal to 1. I mean, intuitively, this is easy to guess. That's what I'm trying to say. But proof is going to be, you see, it will be somewhat lengthy. Okay. To prove this, of course, assume that X is not equal to Y, otherwise there is nothing to prove. So we assume X is recurrent, Y is different from X. Now to prove Y, using the previous corollary, we may prove GYY equal to infinity. That is, the expected number of visits to Y starting from Y itself is infinite. So we now make a tentative assumption. Suppose we can find integers n0 and n1 greater than or equal to 1, such that P super n0 xy is strictly positive and P super n1 yx is strictly positive. Recall that this means probability of going from x to y in n0 steps. And similarly, this is probability of going from y to x in n1 steps. So we temporarily assume this. We will prove this later. And also in what we are going to see now, summation and expectation will be interchanged. The order of, since we are dealing with the discrete random variables, this will also be a sum. And that thing is justified because all the terms we are going to deal with are non-negative. And when you deal with non-negative terms, the interchange is justified with the understanding that if one side is finite, the other side is also finite. And if one side is, and they are equal. And if they are infinite, if one side is infinite, the other side is also infinite. Okay. Okay. So now GYY. So we want to prove that this is infinite. So by definition, it is expectation of the random variable ny. When y is fixed, ny is a random variable. Oh, this should be equality sign. Sorry, this should be equality sign. Remember that ny is this summation over n I sub y of xn. That is the number of visits. So here we have interchanged the summation and expectation. And E sub y of this indicator function of the singleton y of xn is precisely the probability of reaching y from y in n steps. You know that expectation of the indicator thing of a set is the probability of that set. That is the thing we are using here. And of course, the summation n going from 1 to infinity. This P super n yy is precisely this. And this summation is n going from 1 to infinity. So that will be greater than or equal to summation going only from n0 plus n1 plus 1 to infinity. So now this term we rewrite as, instead of calling this as n, we say it is n0 plus n1 plus 1, and now we make n go from 1 to infinity. And you know that this is, say, p to the power n0 plus n1 plus n, that matrix. So we want in that, for that matrix, the term corresponding to yy. Okay. Now we know that matrix is nothing but p n1 product p n product p n0. So if you write this, you have to write this entry in terms of this thing. It will involve, forget about the summation here. It will involve this kind of terms, but not just with xy. It can also vary over some z here. So we take some particular elements in this summation. So that is why greater than or equal to. When you want to write down this yy term corresponding to this product matrix, that will involve lot more terms than this. All are non-negative. And in this one and this one, that the first and the third, they don't depend on n. So they will come out of that summation. So you are left with p super n1 yx, p super n0 xy, summation n going from 1 to infinity, p super n xx. And this is nothing but, just like how we got this step, this is nothing but gxx. Now we know that x is recurrent, therefore gxx is infinity. And also we are assuming that these two guys can be chosen so that these are strictly positive. See here, we are assuming that. Consequently, this is infinite. Therefore, y is recurrent, provided we establish this. So that's what I have written here. So gexx is infinity because of recurrence of x, and as this. So we get that the last equality here due to those facts. If you want to copy down, note down that, please do. Okay, now let us attend to these things and also the other assertions. So as by our hypothesis, y is accessible from x, that is x leads to y. Therefore, there exists an n such that p super n of xy is strictly positive. If you choose one such n, this requirement will already be satisfied. one of the requirements. But we do it slightly differently because we need it for other purpose. So instead of just choosing any such n and call it at n0, we take the minimum of such n's. There exists at least one n because that this x leads to y guarantees that. So n sub 0 is minimum of all n greater than or equal to 1 such that p super n xy is strictly positive. In other words, this n sub 0, n0 denotes the first time point when starting from x, the Markov chain comes to y.
So it is hitting time, right?
Pardon?
Hitting time, right, sir?
I mean, that would be the sort of hitting time, you are right. But here we need it for some purpose. I'm not just calling it hitting time. Yes, you are right. It is the hitting time. Hitting time of y starting from x. Correct. Absolutely right. Okay. So what that means is, since we are, choosing this as the minimum for all k less than n, p super k xy is 0 for all k from 1 to n0 minus 1. And p super n0 xy is strictly positive. And what does this mean really? There exists points y1, y2, y sub n0 minus 1 such that probability x1 equal to y1, x2 equal to y2, x n0 minus 1 equal to y sub n0 minus 1, and x n0 equal to y. That's because this given x0 equal to x. And this probability can be written in terms of our transition probability matrix. We just write it up. Starting from x, first transition is to the point y, and then from y to y2, y1 to y2, and so on. So this is p sub x y1, then product p sub y1 y2, p sub y2 y3, dot dot dot, p sub y n0 minus 1 y. And since this is, this is positive because there will exist something. These things may not be unique. This is one route. Going from x to y in n0 steps, there can be other routes also. And this equation we denote by asterisk. Observe that, remember that we have taken n0 to be the minimum of those guys. None of these yi's, intervening yi's, can be either x or y. Say if, for example, y2 is equal to x, coming back to x in 2 steps, then you can also go by just from, you need not require n0 steps, n0 minus 2 steps you can go. So none of these yi's can be either x or y. For otherwise, it would be possible to go from x to y with the positive probability in less than n0 steps, contradicting minimality of n0. Okay. So the next part of the proof of this theorem is that we want to prove rho yx equal to 1.
We have not established the existence of N1, right?
Yes, it will follow soon.
Okay.
These are all steps towards that. Yeah, you are right. We have to establish the existence of n sub 1. Actually, it will follow once we do this. That is clear, right? If we prove that the rho yx is equal to 1, then there certainly should exist one n1 so that p super n1 yx is strictly positive. Okay. Okay. So this we prove by contradiction. Suppose rho yx is strictly less than. So let y sub I going from 1 to n0 minus 1 be as in that asterisk above. So now consider the probability x1 equal to y1, etc., etc. X n0 minus 1 equal to y sub n0 minus 1. X n0 equal to y. And after that, xn not equal to x for any n greater than or equal to n0 plus 1. Okay, so what we are considering here is basically, see, we have already remarked that none of these yi's can be equal to x. And by our assumption, y is also not equal to x. So this will basically be the probability that starting from x, the Markov chain never comes back to x. Okay. So the idea of the proof is, so if rho yx is strictly less than 1, we will, using that, we will show that this probability is greater than 0, which would contradict x is recurrent. Okay, so that is why the contradiction is going to be arrived at. Okay, so this is a conditional probability. We write it out. So that is probability of the intersection of all this numerator and the denominator. So that is what I have written here. For lack of space, so this portion has got chopped off slightly. The notes, it will be there. So probability of that numerator, that is a numerator, divided by probability x0 equal to x. So now the numerator on the right side here. So that we are considering it as, it is a thing concerning what happens as sort of k goes to infinity of this guy. So that probability is going to be limit k going to infinity, probability x0 equal to x, x1 equal to y1, etc., etc. X n0 minus 1 equal to y sub n0 minus 1, and xn0 equal to y. And after that, xn never visits x, that during the, for the time points, n0 plus 1 to n0 plus k. So this is the probability of, let us say, intersection of all these events here. So we write it as a conditional probability into this. So that is, we condition that thing with respect to x0 equal to x, x1 equal to y1, etc. And finally n0 equal to y. Okay, that's what the conditioning we are doing here. So it is just conditional probability that these guys, this event, probability xn not equal to x for n varying between n0 plus 1 to n0 plus k, given all the other things. And that conditional probability multiplied by the probability of this conditioning event. So we are just using probability of A intersection B is conditional probability of A given B times probability of B. So you can say that this part plays the role of A and this part plays the role of B. Please note it down before we go to the next slide. Okay. So hence by Markov property, time homogeneity, and also using that asterisk, so we get, okay, this. So first here we have written this conditional probability here. We have retained that the left hand side of this expression. So that is equal to this. So the first step here basically is that we have just written this guy left hand side is equal to this. And also we have written the expression for this one, which we already know. That we have got from here. So that is what this is. And of course, here we have also used the Markov property, because in this case, because of Markov property, all this information is irrelevant. This is just conditional probability of this event given just xn0 equal to y. That's what we have. Now by time homogeneity, this is equal to this. And also we are using the fact that limit this thing is also taken into account, and so this. Just like we arrived at a something involving limit going to infinity from here, the reverse step we have done. Together with the time homogeneity we have applied. So as I had mentioned here, this probability is, sorry, not as I have mentioned here, this probability, note that it is, see, the probability starting from y not coming to x at all. So that probability by our definition, it is 1 minus rho yx by definition of rho yx. Yeah, sorry, just again note that here this is equal to this by time homogeneity. Look at just this expression. This expression means the probability of starting from Y and never visiting X. So which is 1 minus rho Yx, because rho Yx is starting from Y coming to X with positive probability infinite. So since we are proving this by contradiction, we are assuming this is strictly less than. So since this is strictly less than 1, this is strictly positive. And from asterisk that we know that each of this guy is strictly positive. So this gives us, so this probability on the left side is strictly positive. So now refer back to the comment I made at the beginning of the proof of this claim. What we have here is the probability of never returning to X given X starting from X. So that implies this probability of never returning to X starting from X is strictly positive, which means rho XX is strictly less than 1. So this contradicts the recurrence of Y. Sorry, recurrence of X. So the claim follows, that is rho Yx is equal to 1. As one of you pointed out, that we have not yet shown the existence of an N1 with the desired property. That now follows. Since we have shown this, rho Yx is strictly positive. What it means is that there exists an N1 such that P super N1 Yx is greater than 0. So the N0 and N1 can be chosen as we wanted, has been established. So consequently, recurrence also follows. And in the process, we have also shown that rho Yx is equal to 1. Note that in the proof of rho Yx is equal to 1, we have not used this thing that Y is recurrent. In the proof of the claim, we have not used anything concerning recurrence of Y. The only thing that remains to be shown is rho xy equal to 1. So that you just interchange the roles of Y and X in claim above. This completes the proof. So a fairly intuitively obvious result, but to sort of establish that, one has to do some work. So this is the last slide for today. So as an immediate corollary, so suppose Xn is an irreducible Markov chain having one recurrent state. So since it is irreducible, from that recurrent state, any other state is accessible. And because of the theorem, it now follows that every other state is also recurrent. So if it is an irreducible Markov chain and having one recurrent state, then all the states are also recurrent, which in such a case, we say that the Markov chain itself is recurrent. And similarly concerning transients. So we will stop here for the day.
Sir, please do post some exercises on this part.
Yeah, I will do that. So the thing is, I want something to accumulate. Probably by early next week, some exercises will be posted. Okay, if nobody has any comment or anything, this thing, I will stop sharing. Now, I would like to have your midterm exam preferably in the first week of November. That would be more or less middle of the semester. So I would prefer, say, for example, the Friday class together with 1 hour later and things like that. If the Friday morning session, if one can finish off, I would prefer that. Otherwise, we can think of Saturday morning.
Post the exercise.
Huh? Somebody said something.
Sir, I have a question. Sir, I have a question. Sir.
Yes, please. I can hear you.
So can you repeat what
No, I cannot. I cannot hear you. I cannot hear you. Please. I am not able to hear you clearly. What are you saying?
Sir, can I type in the chat?
Sorry, I cannot hear you clearly. Please, your microphone, and I don't know whether it's something. It's not.
You can write in the chat if you want.
Okay, you write in the chat. So anything who are wanted to talk? Yeah, when will be the midterm exam? That's what I was discussing. That I would, I suppose, Aranya Baumik, you can hear me now. I would prefer to have it in the first week of November, towards the end of first week of November, and preferably since we have a class on Friday, if it is okay with you people, Friday, let us say, since we are meeting at 10:30, instead we can say have the exam from 10 to 12 or 10:30 to 12:30 or something like that. If that is not possible, similar same on Saturday, first Saturday of November. So since I don't see too many participants are attending this.
Saturday would be preferable because we might have other classes.
Pardon?
Saturday would be preferable because we might have some other classes.
Okay. But okay, so tentatively we'll take it as Saturday. Okay. So I will send but today I find there are only very few students who are attending this session. So I will send an email message concerning this, and one can suitably decide. Okay. So I shall end the session. Okay, take care, all of you. See you next week.